3 servers and a million users. Which user's data goes on which server? The obvious answer, hash the user ID by modulo 3 works perfectly, right up until the moment one server dies. Then in an instant, almost every single key in your system is suddenly on the wrong machine. Your cache hit rate drops to near zero, your database gets hammered, and your site goes down. This exact failure mode is why consistent hashing exists, and it's inside Cassandra, DynamoDB, Discord, and probably every large system you normally use. Let's make the live approach concrete. You take any key, a user ID, a session token, a cache key, run it through a hash function, and take modulo n, where n is your number of servers. Key Alice hashes to 7. 7 mod 3 is 1, so Alice lives on server 1. Deterministic, uniform, no coordination needed. Honestly, a great design for a fixed n. Now, server 1 dies, n goes from 3 to 2, and here's the problem. The modulo of every hash changes. Alice was 7 mod 3, server 1. Now she's 7 mod 2, server 1. Okay, lucky. Bob 12 mod 3 was 0. Now 12 mod 2 is also 0. Also lucky. Carol 9 mod 3 was 0. 9 mod 2 is 1. Moved. Dave 14 mod 3 was 2. That's the server that doesn't exist anymore. 14 mod 2 is 0. So moved. 2 out of 4 here, but with real hash values, roughly n minus 1 over n of all keys moved. With 10 servers, losing one relocates about 90% of your data. Why is that catastrophic? Think about what these keys usually are. If this is a cache, 90% of your lookups now miss and fall straight through your database. That's called cache stampede, and that it can take down a database that was perfectly healthy 10 seconds ago. If this is a distributed database instead, 90% of your data needs to physically move across the network. During an outage, the failure of one node just becomes a cluster-wide event. Consistent hashing fixes this with one idea. Stop thinking of hash outputs as a line and bend them into a ring. The hash function outputs numbers from 0 to maximum, say 2 to 32. Wrap that range into a circle so the max value sits right next to 0. Now, this is the trick. We hash the servers too. Each server's name or IP hashes to a position on this ring, and data placement becomes a simple rule. Hash the key, find its position on the ring, then walk clockwise until you hit the first server. That server owns the key. Alice hashes to here, walk clockwise. She belongs to server 0. Every server owns exactly one arc, the stretch of ring between its predecessor and itself. Now watch what happens when server 1 dies. Its arc doesn't scatter across the cluster. Every key that belongs to server 1 just continues walking clockwise and lands on server 2. That's it. What about keys on server 0's app? Untouched. Keys on server 2's app? Also untouched. Instead of 90% of keys moving, only 1 over n of them move, and they all move to a single, predictable place. Adding a server is the same story in reverse. Drop a new server onto the ring, and it takes over just a slice of one neighbor's world. Nobody else even notices. You can grow the cluster one machine at a time with minimal data movement and zero global reshuffling. But there's a problem hiding in this design. The server positions on the ring are random, and random means uneven. One server can end up owning half the ring, while another owns a sliver. Worse, when a server dies, its entire load lands on exactly one neighbor, which might already be the busiest node. Failures can cascade around the ring like dominoes. The fix is simple. Lie about how many servers you have. Instead of placing server 0 on the ring once, place it 100 times. At position like hash of S0-1, S0-2, and so on. These are called virtual nodes. With enough of them, every server's total ownership averages out to almost exactly 1/n of the ring. And when a physical server dies, its hundreds of little arcs are scattered all around the ring, so its load spreads across the every surviving server, not one unlucky neighbor. And bonus, if you got one machine with twice the RAM, give it twice the virtual nodes. It naturally receives twice the traffic. So how much code is this really? About 40 lines. Let's look at it. The ring itself is just a sorted list of hash positions. The hash function maps any string, a key, or a server name to a number between 0 to 2 to the power 32. And adding a node, we hash it to 100 times. Those are the virtual nodes, and insert each position into a sorted list. That's the entire rule. Removing a node just filters its positions out, and the clockwise walk, the heart of the whole algorithm, is these two lines. A binary search, find the first ring position greater than or equal to the key's hash, and if you fall off the end of the list, wrap back to index 0. That wraparound is the circle. Here's what happens when we run it. 100,000 keys, 5 nodes, and each node holds roughly 20%. Not perfectly even. You can see server 1 got almost 23. That's the randomness of 100 virtual nodes. Crank it to 500, and this tightens right up. Now we kill server 2. 18,887 keys more. 18.9%, 1 over n, exactly what the ring predicted. With modulo hashing, that number would have been 80%. So where does this live in the real world? Amazon's Dynamo paper made consistent hashing famous. It's the backbone of DynamoDB's partitioning. Cassandra uses virtual nodes exactly as we described. The token ring is core vocabulary for anyone who operates it. This code used consistent hashing to spread trillions of messages across database nodes, and your CDN, your load balancers, sticky sessions, your UDIS cluster client, ring hashing is quietly doing its job in all of them. Once you see the ring, you see it everywhere. Next time, we take this ring and actually build a distributed key value store on top of it. Replication, failure detection, the works. Subscribe if you want to catch that one.